Welcome to video 2 of lecture 3 on evolvable hardware. So the previous video on this lecture, we gave some background into variability and ideas of designing a chip which will allow us to deal with variability and maybe faults and do partial reconfiguration actually on the fly on a device that looks a bit like an FPGA with extra functionality. So this was the PAnDA chip, if you remember, and what this video talks about is in somewhat more detail what the PAnDA chip looks like, what it consists of, and a simple application, in fact, related to reliability and related to fault tolerance. So let's move forward and see what we've got here. So if you remember this picture from a few videos ago, and this is a generic loop of our evolutionary system where we have a population which are put down onto hardware, where the hardware is then evaluated to give us a fitness score, which then uses evolution, selection, mutation, mating, maybe crossover to back to a new population. So the idea on the PAnDA chip is, so here's our PAnDA chip here. So it's the same focus, but of course everything we're doing now is actually on the chip itself. So once we've downloaded a configuration onto the PAnDA chip, it can be evaluated. Once that evaluation is done, then we can do all sorts of nasty things to the PAnDA chip to do with crossover and mutation to get a new population PAnDA configurations. So nothing new there, really. Our loop's the same. The only difference is that we're performing the evolution on this new device. So what does this new device look like? So at the highest level, at the top level, the thing that you would see initially, it looks very much like an FPGA, as you've seen it in various parts of your programs over the last few years. So we've got, if you like, a processing cell, and we've got configurable networks, which allow us to connect outputs of cells into inputs of cells in various ways. So very much, as I said, a kind of a common structure. But if we look a bit deeper now, if we look a bit deeper into what a cell looks like, so a cell is made up of a number of configurable logic blocks. So probably still quite similar to what you're used to. So configurable logic blocks, which are connected onto, again, a programmable network configuration structure, which allows to connect outputs of CLBs directly to others or ones that are further away. Okay. Again, if we have a look a bit deeper now, a bit lower down at what a CLB looks like on the PAnDA chip. So this is where things start to change from what you might have expected. So down at the next level, we've got configurable analog blocks, CABs. Okay, so each CLB consists of a number of CABs, configurable analog blocks. So what's a configurable analog block, I hear you ask? Well, if we look a bit deeper, then it looks like this. So let me just talk in a little bit more detail about what this looks like. So each transistor in this configurable analog block has got a gate. So over here on the left, it's got a source connection at the top here, and it's got a drain connection. So that's as you'd expect from a transistor. What's different is what's connected to the gate, source, and drain. So what you'll see here, in fact, even though it's one transistor from the outside, okay, one transistor from the outside, it's actually made up of 7 transistors, so M0 to M6. Okay, and these can either be PMOS or NMOS transistors. In this case, this is looking at a PMOS transistor made up of 7 PMOS transistors. And what the configuration memory can do, the configuration bits, so the thing that evolution would have a handle on, is it can either open or close these switches. Okay. And so what you'll see here is that the drains are all connected in parallel, the sources are all connected in parallel, and therefore if we close a switch here, we're connecting the gates together. And so what you've then effectively got is 2 transistors in parallel, and the effective characteristics of that is it's similar to having a transistor whose gate region is the width of both of those transistors added together. So if you connected 2 10 nanometer gate transistors together, they would effectively have a gate width of 20 nanometers. And what we saw in a previous lecture, in lecture 2, was that by changing the size, the functional size of how the gate is built up, it changes the characteristics of our transistors. So what we can do here is by doing lots of different combinations of switches, and of course we could close all 7 switches, which would make quite a large transistor because we'd be connecting all those gates, adding them together, or we could do different combinations of those. Okay, and by doing that, through the configuration memory here, it allows the PAnDA transistors to change their characteristics in situ, if you like. So we haven't got to go back to the fab and build new transistors. Obviously, there's a minimum size, so whatever the smallest transistor is, but it does allow us to increase the size if we need to, if there's a variability issue, if there's a etc. etc. So let's look at what a configurable analog block looks like, a CAB. So it's made up of a number of these transistors. Okay, remember each of those transistors can be configured. So the size of the transistor can be configured. What this configuration allows us to do, so each CAB is, from the combinational point of view, we'll see in a minute there's a sequential one as well, but for each combinational CAB, the structure always looks like this. And this allows us, it's got a structure of P-type and N-type transistors, which allows us to design and create common combinational logic structures that you'd expect to see in a circuit. So each one of those looks like that. And so this shows the configuration, in this case 8. So using this structure allows us to configure it in one of 8, where it's actually 16, because we can have standard or inverted functions of standard logic gates like NAND gates, NOR gates, inverter, a simple buffer, and slightly more complex logic functions. So we can configure this circuit into one of these functions, and then we can change the characteristics of a NOR gate, for example, by switching in and out different transistors. And we have a similar but slightly different structure to allow us to create sequential logic blocks. Okay, so we've got 2 types of CAB, a combinational one and a sequential one. And if we put all of that together, this is a picture of what the PAnDA architecture looks like. So if we go from in this case, the bottom, but it's the highest level function. So we've got our logic elements at the top level, our cells with lots of connectivity between them. If we look at a logic element, then it's made up of a configurable logic block, a CLB. And if you can just see there, each one of those is made up a series of C cabs and S cabs. So a C cab along the top line there is a configurable, a combinational analog block. And that's got the structure we just saw, which gives us a number of standard logic functions that we can have. And it's also made up of a sequential configurable analog block, which is shown over here pictorially. You can see if you compare the blue box to the green box, they're slightly different. The devices, the transistors are connected slightly different. And this is to allow us to implement some sequential logic, which is shown over here, like multiplexes and things like that, which allows us ultimately to build up things like D-type flip-flops. And every single transistor in both of these, whether it's an S-cab or a C-cab, looks like this. So it's a configurable transistor block. So what you'll see now is, rather than what we're used to with an FPGA, is actually doing configuration down at this level. We've got much more tight control over the configuration of our PAnDA architecture, which hopefully will allow us to, post-fabrication, allow us to deal with variability across the transistor. So if we've got a transistor which has got a slightly different characteristic, we can kind of fine-tune that. We can fine-tune that by doing that. Okay, so let me show a slightly different use of the PAnDA device. So rather than related to variability, this one's related to fault tolerance. So if you've got faults actually on your on your FPGA, or in this case in your PAnDA. So if you look, this is what we've just seen. This is a combinational block with P-type and N-type transistors. And remembering each transistor is made up of our configurable transistor. So what we're going to do is we're going to test this circuit by inducing some faults and seeing whether evolution can find new ways around faulty transistors, individual transistors within this block here. So the way we find the fitness function to decide how good the circuit is by just creating the truth table of the logic function, where these are the voltages which represent logic 1 and logic 0, and we just sum up the correct outputs on effectively a truth table to see how good it is. Okay, and we're also looking at propagation delay and dynamic power. So we're using evolution to look at a number of objectives. As we've seen before, we can do multi-objective evaluation. So what we're going to look at here is a NAND, a 3-input NAND gate. Remember, this is one of the configurations we can do easily on the PAnDA chip. So let me just explain in a bit more detail what these colorings of the boxes mean. So if a box has kind of got wavy lines like this one, it means it's enabled, and what that means, it's a functional transistor. So it's acting as a functional transistor within the circuit. If it's clear, then it means it is always conducting. So it's not really a functional transistor anymore. It just conducts input to output. And if the box is shaded out, so if it's a darker box, then it means the transistor in that point is always insulated. So it's not letting any current through. Okay, so this is our circuit for a 3-input NAND gate. But what we've done here is, you'll notice where there's an X, there should be a transistor there. But in fact, what's happened is we've induced a fault. So we've created that transistor to be faulty. In this particular case, we said, okay, it's going to be conducting. Okay, but not conducting because we want it to as part of the circuit, but conducting because there's a fault there. We're inducing a fault in that particular transistor. So if you draw maybe a more conventional transistor diagram of that, this is what the circuit looks like. Okay, so we've got a number of transistors going in. So we've got an input going into a transistor, input C, which is there. And we've got inputs A, B, and C going into these transistors, which are shown down here. These transistors are conducting, so we don't see these on this diagram, etc. with all of the others. So the issue now is there should have been a transistor here, but we've short-circuited it. So what you'll see now is effectively the output through one path is connected up to the rail. Okay, so this is unlikely to work as a NAND gate anymore, because one of the transistors is short-circuited and is connected straight through to that. So one of the nice things about the structure on PAnDA is we can do this. So we can actually configure these transistors to be either working or conducting or insulating to allow us to build up circuits. Okay, so that was the issue that the evolution had to play with on the transistor circuit of the PAnDA chip. So yeah, this is this circuit again. So what we did was we ran an evolutionary algorithm, and it was, as I said, it was looking at functionality, but it was also looking at power and propagation delay across the circuit. And what it did was it reconfigured the circuit that should have been like this to this circuit. So, and what you'll see now is we've got a typical CMOS configuration where we've got inputs going in series to transistors and inputs going into parallel to transistors, and that's typically how you'd expect a CMOS device to look like. So what it's done now, if you compare the circuits, okay, so it's now made this transistor functional with an input of C. It's made this transistor conducting into there, but B now, instead of B going into there, B now goes into here. So we've got a similar sort of structure, but it's reconfigured both where the inputs are going into in this top half here to give us back to a functional circuit. So that was all done with evolution, but also using the extra functionality that we've got on the PAnDA device. If we just look at the output of these two circuits, so this is the input pattern of our three inputs A, B, and C up here. What you'll see here is so this is when the fault was injected, and there are a couple of things to note here. So the first is V out is while it's trying to be dragged down, because it's connected up to that rail voltage, it never really gets down to less than about 0.5 of a volt, which isn't going to be a logic 0 in our system. And the other thing to note is the output current. So the output current is relatively high all the time, because of course it's drawing current down from the supply voltage. When we've repaired the circuit, okay, what you'll now see is the output has really a quite nice distinction between logic 0 and logic 1. That's now working quite nicely. And you'll see that the average output current has reduced significantly compared to here. So if you look on the scale, we're talking about 10 to the minus 6, whereas up here it was 10 to the minus 4, 10 to the minus 5. So the output current is reduced, and we just get pulses when the circuit is actually changing, which is what you'd expect. But the average current level has come down nicely, and the functionality of the circuit is working rather well. So that shows that actually not only kind of pictorially, but also functionally, the circuit worked nicely. Okay, so as I said, we actually fabricated this chip. We fabricated this design. So this is a slide of what the chip looked like. So the actual chip that was designed. So it's got this particular chip featured. So it's got 400 CLBs, and each CLB comprised of 8 cabs. And if you remember, the way we've done it is 4 of those are for sequential circuits and 4 are for combinational circuits. It was fabricated on 64 nanometer technology, so not the most up-to-date technology, but the one that we could afford on this project. And the chip design was around about 13 square millimeters. Okay, so that was the device. How do we use it? Well, of course, you get shipped a chip, and that's all you get. So there's quite a lot of infrastructure when you design a chip to actually get that working. So the way we did it is we had an FPGA, standard Xilinx FPGA motherboard, which was connected to a PC, which was where all the programming went on and was downloaded. And then on that board, we designed a motherboard just to plug in to the sockets on the FPGA board. And then we built a number of daughter boards, which allowed us to put our PAnDA chip effectively connected through this to the PC. So that allowed us to download programs to test the circuit, etc., onto that. So it's it's more work than just designing a chip when you do such things. Okay, so in summary for this chip, it was allowed. We designed it to use evolvable hardware to alleviate the effects of variability, and also we'll see in fault tolerance as well. The new architecture allows reconfigure at many levels. So of course you can still reconfigure at the top level, at the cell level, but it also allows you to go down to the transistor level to actually tweak the characteristics of the device. Okay. And certainly it's a really nice device for looking at future evolvable hardware research. The overhead on it is probably a bit too much for a production FPGA at the moment, but who knows for the future. And finishing off, here's a couple of papers that we produced that talk about more detail about the PAnDA device and some applications on the PAnDA device if you're interested in looking at that further. Okay, thank you for that. And there's one more video in this lecture to see, which we'll talk about next time. Okay, see you then. Thank you. Bye.